Right, today we're going to be looking at something called a natural logarithm. Now, natural logarithms are similar to logs of base 10, where we use a specific base as our log. Okay? And the base that we use it comes from the special exponential constant called e. All right? So e is very similar to pi in that it's a constant number, and instead of writing this constant number the whole time, we would rather just write pi, and it has a value of roughly 2.718. And I guess one of the most common questions people would have is, where does the number e come from? Now, there's quite a few ways you could come up with it, right? It is a mathematical pattern that appears, but one of the more interesting ways to see this number is by thinking about it as the maximum rate of exponential growth in a population. Right? The maximum way a population could grow in relation to itself. So if we take the compound interest formula that we already know, where we take a starting amount and we apply some kind of compound interest, and what we're going to do is we're going to imagine we're investing $1 at 100% interest for 1 year, and we want to consider what we would get out the other side. So just taking our formula where we go a equals, right, we're going to consider $1, so p is just going to be equal to 1, and we're going to take 1 plus, and it's 100%, so the rate would be 1 to the power of 1, which is 2. And that makes sense. If you invest $1 at 100% interest for 1 year, you will get exactly double the amount of interest, or double the amount, so you will end up with $2. Now, we all know that the banks can pay interest at better rates, and so we can consider, what if we invested this amount of money at 100% interest, except it was compounded twice a year? So we get 50% in the middle of the year and 50% at the end of the year. And so instead of getting 100%, we'll get half of that. And instead of having 1 period of compounding interest, we'll have 2. And what we end up with is $2.25. So we, somewhere in the process of compounding an extra period, we've ended up with 25 cents more. And we can continue this, right? And we could say, well, logically, most banks don't pay interest twice a year, they pay interest every month, right? So we take the same 100%, we're going to divide it by 12 months, and we'll have 12 compounding periods. And we'll end up with $2.61. Now that seems quite a massive jump. So we've gone from 25 cents to 61 cents different just by compounding for an extra 10 months. So the idea is that, well, could we continue this trend? Could we continually increase the amount of money we could gain if we compounded interest at a higher rate? And we can say, well, what if we don't want to compound every month? What if we want to compound every day? So 365 days in the year. But that's not enough. What about every hour? What kind of interest would we get then? And so if we multiplied this, we end up with 2.718279, etc. Right? And that's quite an interesting observation to make. We've only gained an extra 10 or so cents, even though we have increased the compounding period significantly. And another thing you'll notice is this is very similar to the number that I introduced you to, and that is E. So what is E? Well, it's the idea that if we took an amount of $1 and compounded it at 100% interest, but we invested it at a period approaching infinity. In other words, we really invested it for a very, very, we wanted to calculate the interest at a micro level. Right? Obviously, our periods would also approach infinity, and the number we approach as we take the limit is 2.718, which is this magical constant e. So for the time being, natural logarithms are no more, no less than just taking a very special base when we look at logs. Okay, so if we had y equal to e to the power of x, I want you to remember that this e isn't some variable. That e represents an actual number. It represents 2.718279, etc. Just like pi, instead of writing pi, we write e, so that we can use the exact value on our calculators. Okay. Now, when we look at logs, right, we log to a specific base, and when we log to this base e, again remembering we could have log base 10, we could have log base 2. So when we're saying log base e, we're saying we're having a base of 2.718, etc. Okay, but when we take logs to base e, we call them the natural logarithm. Okay, and we further abbreviate that. Instead of writing log base e, we abbreviate that to the natural log. So we replace log e with the letters ln to specify this is the natural log. Okay, and just like all other exponentials and logarithms, they have the same rules. So if we write y equal to the e to the power of x, we can rewrite that as x to the power of the natural log of y. And again, this natural log is just representing log base e. And in a similar fashion, we could think of the inverse function is the natural log of x. So just looking at some simple examples, right, we just need to wrap our heads around the fact that we're not dealing with a variable, we're dealing with a number. Okay, so e is an actual number, and it's on your calculator just like pi. In fact, it's right next to pi on your calculator. So if we want to take e to the power of 3, an even better number to or button to use in your calculator is just above the natural log button. Just above that is the e block button, e to the power. So here we're just going to go e to the power of 3, and we'll get 20.08, which we can round to 3 significant figures, like so. Okay, and then in the next question, we're looking at the natural log of 3. So on our calculator, there is a button for the natural log. So natural log of 3. In other words, what we're saying is log base e of 3. What do we raise base e by to get 3? And the answer is 1.0986, which can be rounded to 1.10. Right, then some simple questions where we get asked to find without a calculator. So we have the natural, or e to the power of the natural log of 2. Now we need to remember that the natural log is actually just log base e. Okay, so we have log base e of 2, and we remember that if we had an exponent raised to the log with the same base, we could drop to whatever the value was. And so this can just be simplified to 2. And much the same here, we have e to the power of the natural log of x, and in exactly the same sense, this is e to the power of log base e of x, which can be simplified to x. Right, here we are asked to solve to 3 significant figures. We have an exponential equation with different bases, so we're going to rearrange, remembering that this is the base, this is the exponent, this is the value. Now rearranging, we could write this as log base e 18 equal to x. However, we don't write log e, we write the natural log of 18 equals x, and so x is equal to 2.89. And over here, we have the natural log of x. Okay, so we are being asked to calculate the value. So here's the value. The base is hidden, but just like log 10, it's implied that it's e. And here's the exponent. So rearranging, we could write this as e, because the base is e, to the power of 5 is equal to x. Therefore, x must be equal to 148.